Okay, the type of research we do at KTH is based on this work by Michael Gretzel in Switzerland that was published in Nature in 1991. It's one of the most cited papers today. If you look at the research field as a whole, there are about 50 articles in scientific journals per week, and there are about 5 to 10 patents globally in the field, also per week. Current world record is about 12%, and well, there's still quite a lot to do in terms of stability. The main advantage of this type of solar cells is that it's sort of kitchen chemistry, which means it's very inexpensive to produce. You can use screen printing techniques industrially, etc. And even, let's say, at home, you could easily make a solar cell based on, for instance, spinach or tea or something like that, and produce 0.5% of efficiency. The big problem you will have will be stability, and that's also the problem we are fighting with. And when I say we, it's something called the Center for Molecular Devices. It's a center based at KTH and Uppsala University, where we're different research groups working together trying to solve this problem. And the head of this center is Anders Hagfeldt at Uppsala University. And we go in with different types of competencies in order to try and make these cells more stable and more efficient to try and meet these targets. And at KTH is my group working on electrolytes and interfaces, and there's also the group of Li Cheng-sun working on sensitizing dyes. So this type of solar cell, it's a traditional electrochemical cell. Basically consists of 3 parts, 2 electrodes and an electrolyte in between. Just like a battery or a fuel cell, the difference here is that one of the electrodes is photoactive. It catches the solar radiation. And this is the way it works. You have the working electrode, the photoactive electrode here, and the counter electrode there. There is some light coming in. It's absorbed by the dye. The dye is excited. It injects the photoelectron with lots of energy into a semiconductor layer. It goes back to the back contact. And this excited electron you can put to work. And then the tired electron is put back by the counter electrode, and the redox active component in the electrolyte carries it back to the dye and puts it back, and it's ready to absorb light again. So every sensitizing dye here is activated approximately once per second, and each of these nanostructured particles at full solar radiation contains something like 30 photoelectrons. That's about it. So what do the cells look like in real life? Well, these are the so-called lab cells. These are our working horses where we test new components and characterize what's happening with the photoelectrons. Why don't all of them go and are available for extracting energy and so on? And at the same time, we work together with IVF in Gothenburg in upscaling and using more screen printing types of techniques. So just very short on the research on the different parts, the 3 parts, the 2 electrodes and the electrolytes. Well, there's lots of work being done on the working electrode here. Typically, is some sort of nanostructured material, and I said that maybe 50 papers per week are published in the field. 90% of these, maybe 45 of the 50, concern either this type of material or the sensitizing dye that you're using for the cells. And these can be either organometallics or they can be organics, as I will show soon. But the target here is to be able to catch as much of the solar radiation as possible. And the big challenge is to move into this field here in the infrared or close to red region, because there are lots of photons that you want to catch. If you just go for the UV, visible is too little and limits the efficiency of these. There's a strong drive to go from the organometallic to more robust organic dyes. And this is one produced by the Li Cheng-sun group here at KTH. So this is a strong field here as well. So there's lots of work going on the various components. Counter electrodes are sort of forgotten. Not very much work is being done there. We are working a bit on new carbon materials, but still it's a small field. And then of course, what you would like to achieve is to have a double electrode active, which is photoactive here. But that's really, really challenging. And today, the best ones are doing less than 1%. And you might think it's ridiculous, but if you look at photosynthesis, for instance, it's less efficient than 1%. So maybe not for technical application, but it's still not so bad. We're working a lot with electrolytes. We work with something called ionic liquids simply because they are non-volatile, which means that you don't have the problem with evaporation and so on. And we're spending a lot of time on that. But we also work on sort of quasi-solid and solid types of electrolytes, because that's sort of one requirement for actually these cells to be commercially available. And if you look at what the challenges are in the future, well, there are two. One is basically finding good and new materials for making them useful, and the other one is to fit them all together. And that's also one of the reasons why we work on this as some sort of network where different competencies go in and do different parts. And that's basically the solar option, and I'm ready for questions.